Okay, so we have, I posted this document, midterm topics. We've got a midterm next week, so I thought I'd just kind of go over. Okay, so it'll be here in class, pen and paper exam. I will send out a seating chart. Are there letters or markings on your desks? It's just written nothing, right? It's just blank. Okay, so I'll just come up with some arbitrary numbering system for the desks, and we'll use that. Okay, so it'll be done here in class. You'll need a calculator, definitely, and then you will be allowed to have one sheet of notes. Okay, one sheet of notes. You can write on the front and back. You can handwrite it. You can type it. Put your name on it, and I will ask you to submit your note sheet with your exam. So if you want to keep a copy of your note sheet, make sure you take a picture of it yourself or something. Okay. And note sheets have to be your own creation. You can't just photocopy someone else's note sheet. Okay. So it's got to be your own. All right, and then and yeah, I'll send out a seating chart. So just probably the day before. They'll tell you you'll sit in this, sit in seat B5 or something like that. Okay, so what can you expect? You'll have some vector-based calculus. So I'll give you some kind of function. That function will be written in vector notation, and then I'll ask you to find the gradient of the function with respect to a vector. You can kind of, as far as practice goes, you can take a look at, say, the OLS function in vector form and see how we took the gradient with respect to the vector W. You also did something similar in homework 1 where you had weighted least squares, and you took the gradient with respect to W there, things like that, okay? Another problem is you will do some gradient descent, and you will do this manually, okay? So I will provide a function. It'll be like a function of 2 variables or a vector of length 2, okay? And I'll provide some arbitrary starting location and some kind of learning rate, and using that, you will calculate, what's the updated location at the next iteration, what's the updated location at the next iteration. So we have an example of this in the lecture notes, where I had kind of that contour plot of the ellipses, and then we just started off at one location, and then we drew an arrow, and then we drew a second arrow, okay? And you'll just have to do it kind of by hand. So probably you'll just figure out your partial derivatives with respect to the first variable and the second variable, and then add those, okay? There will be a very simple kind of regularized loss function problem. I'll provide this tiny little data set, maybe 3 data points or 4 data points, just so it doesn't become super tedious. And then I will provide an equation for a potential line of fit. So it'll say y hat is equal to this, w0 plus w1 x1 plus w2 x2 or something like that, okay? Or maybe t or whatever. And you'll find the OLS loss. So you'll take the difference between the actual values and their predicted values, square them up, sum them, or take the mean of them, and then you'll calculate lasso loss, and you'll calculate ridge loss. All right, and then just again a friendly reminder: don't include the intercept term when you calculate lasso or ridge regression penalty terms. Okay, and then lastly, I will have you do some leave one out cross-validation. So in the lecture notes, I had this example where we had 4 data points, and we removed one and we fit the model to the remaining 3 data points, and then using that we calculated the cross-validation error. And so for this, there will be maybe a couple, I'll have like 2 competing models, and I will ask you to perform leave one out cross-validation. So you'll find, you know, what's the residual with this model and what's the residual with that model. So, you know, when you do leave one out cross-validation, I'll give you what is the model when you have n-1 points. So if you have like 4 points, I will fit the line or fit the model to the 3 remaining points, and I'll say this is what the coefficients are there, and using that you'll have to figure out, you know, what is the predicted value for the point that we left out. Okay? So a little bit like you had a homework problem where you fit, you know, a linear and a quadratic and a log and a log-log model and things like that. So this is just kind of like a miniature version of that, just like 3 or 4 data points, only 2 competing models, but you'll do it by hand rather than using R's LM function and predict. Okay, so just have that. And then I'll have a handful of conceptual questions. Some of these conceptual questions will be taken directly from the notes, and others will require you to do a little bit of thinking about, you know, what are some of the implications of this, I guess, of this definition or of this statement. Okay. All right, and that's what you can expect for your first midterm exam, which is just in, I guess, 5 days. Okay, on Wednesday. All right, so that will be yeah, right here, 8 a.m. And we'll do that. Okay, let's go ahead and take a look at today's lecture. Happy Friday, everybody. All right, I wrote a quick review quiz, but not really a quiz. All right, so we are introducing neural networks, and we talked about kind of forward feed. How do you go from your inputs x to the predicted value y hat? And it involves multiplying your input matrix x by your first weight matrix w1, and then after you do that, you apply an application function to those outputs, and then you take those values, that matrix, the A matrix, and you multiply it by your second weight matrix w2. So the first question is, what are the dimensions, if this is our neural network with a kind of a 2 nodes, 3 nodes, 1 node structure, what is the dimension of w1? What are the dimensions of x, w1, w2, and say y? So, well, x is easy. We have n observations, so we're going to have n rows. We have 2 columns, so that's going to be n by 2. But what is the dimension of the w1 matrix, your first weight matrix? 2 by 3. 2 by 3. And then what about the dimensions of w2?
3 by 1.
3 by 1, right? So you take how many, basically the number of rows will be how many nodes you have on the layer coming in, and then the number of columns will be how many nodes you have on the layer going out. So here we have 2 coming in, 3 going out, so that's going to be 2 by 3. Here we have 3 going in and 1 coming out, so that's going to be 3 by 1, exactly. Okay, and so those are your answers. All right, so so this is what we have. We've got our neural network. We have our x values, and then we have 6 kind of coefficients, 6 weight terms arranged in this 2 by 3 matrix, and then we have kind of these 3 terms in the W2 matrix. And so this is what we are doing. And when it comes to training the neural network is figuring out what are the values that we should use for these terms here. And so we've got kind of 9 values that we need to optimize over. So you have this kind of this, conceptually, you can think of it as a 9-dimensional function, which is kind of impossible for our brains to visualize. But we have this 9-dimensional function, and we want to find the kind of the right combination of these 9W terms so that the sum of squared losses, or the loss function, sum of squared errors, mean squared error, is minimized. Okay, so do we make W11 really big, or do we make W11 really negative, or something small, or something? We're trying to figure this out. What size value do we want to do? And so this is a really hard question for us to solve, and I don't know if there's some kind of analytic solution. So we're going to use gradient descent to kind of solve it. Also, just keep in mind, we also have these activation functions, this sigmoid or logistic activation function, and what that does is you get this logistic curve that varies between 0 and 1. And if you put in all of the different terms, our predicted values are y hat. Okay, so remember, the only things that we are kind of messing with are the values inside W1 and W2. Those are the 9 terms we have. We are not changing any of the x values. The x values are our observed data. We're not changing any of anything else. So everything else is, if you leave x fixed, okay, then you can change W1, which will affect Z2. We're using the sigmoid activation function, so once Z2 is determined, A2 is determined. Okay, and then when you do A2, we have a little bit of control over what's inside W2, but then that's going to determine Z3, and again, sigmoid activation function, once Z3 is determined, it's going to get y hat. So, important thing to remember, we are not changing or altering any of the observed values of x. That's the data coming in. We treat that as fixed. We only have 9 values, like 9 little knobs that we can kind of adjust, and we want to kind of find the right combination so that that our y hats are as good as possible. And good as possible is going to be minimizing the difference between the actual values y. Actual values y are also set or fixed. They are our observed values, so we can't mess around with the actual values y, and we can only kind of change y hat by a little bit indirectly by changing W1 and W2. Okay, so certainly changing W1 and W2 will affect what y hat is, but we're trying to figure out what values to use in W1 and W2 so that the y hats are as close as possible to the actual y values. That is the problem that we are facing. That's what it means to train the neural network. Figure out what values of W do we need to use so that when we go through this process of forward feeding our data, our fixed observed data, through this, multiplying and applying things, and we get our y hats, what values of W do we pick so that the y hats are as similar as possible to the actual values y, which will thus minimize our total squared error, mean squared error, whatever you want to call it, right? I mean, they're not the same. Mean squared error and total squared error are different, but they are just, one is just a multiplicative constant times the other. Okay, so if you have the total squared error, mean squared error is just that number times 1 over n. And here, just to kind of help our calculations look a little bit cleaner, we're going to take this mean squared error, multiply it by n over 2, just a different constant, so that our loss function is going to be 1/2 of basically yn minus y hat n, or yn hat squared summed up. Okay, so this is our loss function. We'll call this j, and that is the function that we're going to go. And we can see that whatever values of w that minimize j will be the same exact values of w that minimize l, just because one is just a multiplicative constant away from the other. Okay, let me go ahead and give you your first view quiz answer, which is the letter B. B as in bear. Okay. So how do we do this? Well, the way we're going to approach this is we're going to use gradient descent. Okay, so in the ideal scenario, you would take the gradient of this, set it equal to 0, and solve. But that's really tricky because this is kind of a mess. Okay, so taking the gradient and setting it equal to 0 and solving, that's kind of hard. So what we're going to do instead is we're going to apply gradient descent. We will calculate the gradient. We can find the gradient of that thing. But then we're going to, in order to figure out where is the gradient close to 0, where do we reach a kind of a local minimum for the loss function, we will apply gradient descent. We're going to start somewhere, iteratively take little steps downhill, and then hopefully end up at like a minimum value, local minimum, maybe a global minimum. Okay. Now again, gradient descent does not guarantee that it will converge to a global minimum. Doesn't even guarantee that it will converge, right? A lot depends on, what is that learning rate that you picked. If you pick a bad learning rate, it could diverge. There's all kinds of potential problems. However, in a lot of cases, gradient descent does work, and it works pretty well in a lot of cases. But again, there's no guarantees. No guarantees that this is, the right the right way to solve it. Okay, so well, as one might expect, in order to do gradient descent, we got to figure out the gradient. So here is our network diagram again. And what is the gradient? We want to figure out how does our loss function change with respect to changes in each value, W11, W21, W31, and this matrix, and also this matrix and whatnot. Okay, so we have two gradients to calculate. One is going to be basically how does the loss function change with respect to changes in W1? How does the loss function change with respect to changes in W2? And this will be dj dw1 will be a 2x3 matrix, same dimensions as W1, okay? And it will consist of the partial derivatives, dj dw111, dj dw121, and so on and so forth, right? So one thing to keep in mind is that with a gradient, the dimensions of the gradient will always have the same dimensions as the whatever vector matrix that you're finding the gradient with respect to. Because keep in mind, when we do gradient descent, you have either a vector or matrix, and you have it at, say, time, I guess, t, or here, I forget what the notation is, t plus 1. This is equal to your gradient at time t minus, do I use gamma or lambda? I don't remember. Okay, I'm going to just write gamma nabla f of the gradient at time t. Okay, so this thing, in order for you to be able to add this and this thing together, this thing must have the same dimensions as this thing. So if this is 2x3, then this thing also has to be 2x3. Otherwise, we can't do this plus this. Okay, so just keep in mind the gradient to this thing, okay, which here we're calling dj dw1, okay. Yes, maybe I should, I don't know. These are matrices, not vectors. But same idea, okay? If you've got this matrix W, you got this matrix W, which is 2x3, then the gradient nabla f with respect to W1 has to be the same dimensions as W1, okay? So that's what we had. All right, if we had bias terms, you would have to also calculate the gradients with respect to the bias terms, which will be in your next homework assignment, but we'll work through this. So we will we'll work backwards. And so this next part is called back propagation, because we're kind of looking at how do we figure this, how does y hat change when we change basically any of these terms and any of these terms. And so we want to know, how does this hat, y hat change when we change any of these things, okay? And really it's how does, not just y hat change, but how does the loss function change, okay? The loss function changes when y hat changes because it's y minus y hat. So we will calculate the gradient with respect to W2 first, the second weight matrix, right? So our loss function is the difference between the actual values and y hat, okay? And so I have this written like this, and we want to know, okay, how does this change when we change W2? All right, well, summation of this over basically all of our n observations, we can just say, so, you know, the gradient of a sum is basically the sum of the gradients, so that's fine, okay? And just kind of applying, you know, vector calculus rules and whatnot, okay? We ask, how does this change? Okay, well, yn, these are our observed values. These are constants with respect to W2. They do not change because we observe them out in nature or whatever from our data collection. So changing our slopes or our weight terms is not going to have any effect on the observed data that we have. So there's nothing to worry about there. However, the y hats, our predicted values, definitely do change when we change W2. So taking, you know, the derivative of this, we are going to, you know, just power rule, right? So the 2 comes down with the 1/2, cancels it out. I get yn minus y hat n. And now I have to apply chain rule to the y hat n and say, with chain rule we get -1. And then we say, well, how does y hat change with respect to W2? Okay. And then, so keep in mind, what is, you know, our y hats were the results of applying this is our kind of activation function applied to our Z3 matrix. Okay, and so I guess we can, you know, take each kind of term here. So y hat, if you're looking at one observation y hat, okay, y hat sub n, so one predicted value is the result of applying your function to Zn, okay, which was just kind of one value there. And so therefore, when we say, we're going to go back to this thing and say, okay, how does y hat change with respect to W2? We can kind of break this out into more partials, and we say, how does it change with respect to Zn3, and how does Zn3 change with respect to W2? So here we can just say, you know, how does y hat n change with respect to Zn3? Well, that's just because y hat n is the function applied to Zn3. We'll just say, okay, well, that's going to just be f prime of Zn3. Okay, so that's going to be this term. All right, so y hat's just the result of passing Zn3 through the activation function. So it's just the derivative of that. The activation function is this logistic function, 1 over 1 plus e to the negative t. So we have that. And then, okay, so f prime here, this is, we'll just use quotient rule from calculus. So if f is u over v, which we'll treat like this, then f prime is u prime v minus uv prime over v squared. So if this is our function, we'll say u is 1 and v is 1 plus e to the negative t. You go through it and you will say f prime is this, okay, e to the negative t divided by 1 plus e to the negative t quantity squared. So that's going to be f prime there. And so we have this. This is going to be that. And just kind of for, to kind of keep everything neat, I will just replace y hat n with f prime. I'm sorry, the partial of y hat n with respect to Zn3, we're just going to write f prime Zn3 here. Okay, and now we still have to figure out how does Zn3 change with respect to W2. Okay, well, if you look at the matrix, okay, Z is the Z3, that Z3 matrix, which is n by 1, is the result of taking your A2 matrix and multiplying it by W2. Okay. And then if we just look at, say, one observation within, so this is Z3, and this consists of, I guess, Z1, Z2, down to Zn, okay? And this is the result of basically taking your A2 matrix. I don't know how to make this bold. A2, which is n by 3 times your W2 matrix. So this is W1, W2. You basically had 3 terms in here. A11, A12, A13, and so on and so forth. Okay, down to. Right. So if we just focus on one row, it's going to be this times this, right? So we have our A row AN, which is going to be 1 by 3, times W2, which is 3 by 1. So let's just focus on this one value. So then we could say, okay, if this is our one value here, we're looking at just this kind of first scalar value, Z1 or Zn. That's going to be this row times this. What is the gradient of this with respect to changes in W2? Okay. So using kind of our derivative rules, it's going to be, okay, what is the gradient of this with respect to W2? This becomes just AN2 transpose. So we want to say, hey, how does that change with respect to this? It's basically going to become just basically we'll take this and we'll just transpose it there. Okay. Does that kind of make sense? This is just kind of the gradient relations there. So that's going to be how Zn3 changes with respect to W2. It's going to be a 3 by 1. Okay, so I'm going to throw that in there. And so this is what we have. So for each observation, yn minus our predicted value y hat n, we have f prime of Zn3, and then we have the gradient of this with respect to W2, which is going to be AN2 transpose. This over here, this is just a scalar value, okay? And this is a 3 by 1. Now, here, the way I have this is we calculate this for each observation. We do it for the first observation, and we do it for the second observation, and we do it for all n observations, and then we sum them up, okay? And that's how we have it. And that's fine, it works. It would be nice if we can get rid of the summation symbol, because summations, the way you have to implement a summation in code is you have to write a for loop, and you say, for, n I is 1 through n, whatever, and it slows things down. So it'd be nice if we can get rid of the summation. Sometimes we can, sometimes we can't. So can we kind of approach this from a vectorized standpoint and say, yeah, we'll try that out, okay? So rather than just looking at each one individual value at a time, what if we looked at the entire kind of column of y values, okay? And what would happen if we do that, okay? Well, y sub n, which is just one value in y, if we look at all of y, now we have a column that's n by 1, okay? Same thing with the y hats. We have a column of y hats that's n by 1. We look at what z3 is, okay? Rather than just one scalar value here, we're going to get a column of z values, which is n by 1. And then if we think about what is this thing, rather than just one row, which was 3 by 1, so rather than just one row transpose, which is 3 by 1, if I take the entire matrix and I transpose it, then I will get 3 by n. Okay? And if we do that, we go, oh, you know what? The terms don't line up. Like I can't do this matrix operation because I got an n by 1 multiplied by an n by 1 multiplied by a 3 by n. So this does not work in terms of matrix multiplication. And so this is where I say we are going to use matrices as a convenient notation to kind of get rid of the summation signs. But what we are doing next is not strictly linear algebra, okay? So if you take, you took what, 33A, your linear algebra class, and there were things that you had to do and things you were allowed to do and things you weren't allowed to do. We are going to be doing things that would make your linear algebra professors cringe because this is not linear algebra. We're using the convenience of matrix notation to do basically multiplication and addition operations, but it's not strictly linear algebra. So don't get mad at me here. But we're gonna basically, we're trying to say like, okay, if I want to take this idea of here I got 3 numbers and I've got 3 numbers here and I want to multiply them and add them together, like matrix notation provides a nice convenient way to talk about that, okay? But what I want to do here is when I expand the y's, I have this column of n values, okay, an n by 1 column. And then over here, when I expand the z's, I also have a column of n by 1 values. And in matrix notation, we don't have a way to kind of like, how do I multiply these things together? Okay, so basically what I'm going to do is I'm going to just take a step back and just say, hey, let's go back to just this one term, the nth term there. And if these were just kind of, if this is a scalar value, this is just one term, and this is a thing, I could, when I do scalar values, I can just kind of rearrange these things. Okay, I can take the a and bring it to the front, right? And we would agree that this thing and this thing are equivalent, right? This is, if I kind of take this 3 by 1 column here and I slide it over into the front, here this is still, what up here and what's down here, these are equivalent, right? And then so now if I kind of drop the n terms, and again, I expand this into a matrix, okay? That 3 by 1 becomes 3 by n, and then the y column, the y value, this one scalar value here, becomes a column n by 1. And now this matrix multiplication, those dimensions line up, okay? In linear algebra, regular old linear algebra, you're not allowed to take one matrix and just like move it around to another thing, right? Like, with algebra, you can do stuff like that. You can multiplication, you can change the order of these things. But algebra, you're just dealing with these like plain old scalar values, okay? But in linear algebra, we're dealing with matrices, and you can't just rearrange things there, okay? But again, what we're doing is not strictly linear algebra, and I'm just kind of saying like, well, let's pretend this is okay, and I think this is okay. If we just look at one term here, like, can I kind of move things around? I think so. I think that's allowed. Okay, and then if I drop the subscript and I say rather than having a summation, we're going to be dealing with the entire column of n values here, or the entire matrix, which is transpose 3 by n, then that's allowed. Okay, and so now again, we kind of make up a symbol here, thing that doesn't exist in linear algebra. I've got a column of values here, a column of n values for y minus y hat. I've got a column of n values, which is f prime of z3. And I want to preserve, I want to take basically the first value here times the first value here. And then I want to take the second value here, right? When n is 2, I want to take the second value and multiply it by the second value. I want to take the third value and multiply it by the third value. How do we do something like that? Okay? Here I write this, made up this symbol here, and that's going to describe element-wise multiplication down a vector, okay? Which, again, doesn't quite exist in linear algebra, but the computer sure likes to do it, right? Like that's the star operator. In R, you have a vector here and you have a vector here and you do the star operator. It just goes element-wise down those vectors, okay? So it feels like this should be allowed. and so anyway, that's what we have here. And so this is what we have. This is our gradient with respect to W2. Okay, does that kind of feel okay? So if you watch the Welch Labs video, he also kind of does this. He kind of waves his hand and he does it really quickly. But this is what we have. We have delta 3, and we'll call this that. And so the final result is going to be A2 transpose times y minus y hat element-wise multiplied by f prime z3 negative, and so that's what we have there. Okay, let me give you your second view quiz answer. The letter D. D as in dog. D as in dog. Okay, so we're going to do the same thing now with respect to the first weight matrix. Everything starts off the same. Okay, we've got the loss function. We say, how does it change with respect to W1? Well, the constants, or the actual observed values, y's, don't change with respect to W1, but the predicted values y hat do. So we'll apply chain rule, and we come to here. We say, how does Zn3 change with respect to W1? Okay. And so we break this apart. How does Zn3 change with respect to W1? Well, W1 affects A2, our A2 matrix, so we'll say, how does Zn3 change with respect to A2? How does the A2 change with respect to W1? Okay, so kind of very similar to here. Now this time we want to say, how does Zn3 change with respect to A2? Okay, well, now it's going to be Zn3 is this times this, it's going to be W2 transpose. Okay, because now we need to get something in this row form here. So this is what we have. Okay. So we'll throw that in here. How does A change with Zn3 change with respect to A2? It's going to be W2 transpose. Now I want to know, how does A2 change with respect to W1? Okay. So we further split that into, how does A2 change with respect to Zn2, and how does Zn2 change with respect to W1? Okay, so much like the logic that we had before, An2 is just the result of applying our logistic function to Zn2. So the derivative of that with respect to Zn2 is just going to be f prime Zn2. So we'll throw that in here. Okay, I'm trying to keep track of everything I'm doing by doing kind of writing the dimensions underneath of these things. And so we see, oh, you know what, we're going to have to probably do like a element-wise multiplication, because I got a 1 by 3 and a 1 by 3 here. Okay, and so now, now we have this problem. How does Zn2 change with respect to W1? And now we run into this issue. And we say, okay, well, let's just look at one value. Okay, or for one observation in this Z2 matrix. In the Z2 matrix, one observation is actually 3 values. Okay, because when you feed it through the network, there's 3 nodes in that hidden layer. And so when you look at, say, the nth observation in Z, it's a row of 3 values. It's a 1 by 3. The X values for that nth observation is a row. It's one row with 2 values. hours of sleep and hours of study or something. And then we multiplied it by matrix W1, which is 2 by 3. Okay, so we're asking, how does this row vector of length 3 change with respect to changes in a 2 by 3 W matrix, right? How does Zn, the nth row in Z, change with respect to changes in W? And W is a 2 by 3 matrix. This feels a little bit weird, okay? So here I kind of expanded this out and I say, okay, well, what does it look like? If you just look at the nth row in X, the nth row in X is just one row where you have two values. And what we're doing is we're multiplying it by this 2 by 3 matrix, W1, and the result is a 1 by 3 output, right? And this is basically our Z, nth row in Z. The nth row in Z is just this 1 by 3. And so we can kind of use this idea of like, how does the output, how is that affected by changes in any of these things? Like if I change this one top left corner, how does that affect the output? If I change this value right here, or this value, or this value, if I change any of these values, how does that affect the output? And so we can see if I change any of the values in the top row, the way it affects the output is that that change is gonna get multiplied by xn1, okay? If I change it in this value, it's gonna get multiplied by xn1. If I change this value, W13, it's gonna get multiplied by xn1. Okay, so any change in the top row gets multiplied by xn1, okay? Any change in the second row will get multiplied by xn2. So it feels a little bit weird, but if we're talking about this, the kind of the derivative or gradient of Zn2 with respect to W1 ends up being basically a 2 by 1 matrix. Just you take this and you transpose it. It's just going to be the transpose of X, of this nth row in X. Okay, a little bit weird feeling, but it works out mathematically that way. So here I'm going to kind of replace that last term with xn transpose, which is 2 by 1. And again, the dimensions don't line up. Again, we're cheating and doing this thing that's not linear algebra. Don't tell your linear algebra professors that we're doing this, okay? But basically, again, we're just trying to use the matrix notation as a convenient notation for multiplying all of these things and adding them up, okay? We could just keep it in like regular summation form and just deal with the constants so that we can rearrange terms and not run into any trouble. The matrix notation provides a convenience for us as long as we also make up a couple rules and operations as well. So here I'm going to kind of slide this over to the front, okay? And if you think about each of the values in here, we're going to get, so now we have a 2 by 1. This whole thing is a 1 by 1. This is a 1 by 3, and this is a 1 by 3. And so in order to get these to multiply nicely, you know, I got a 1 by 3 and a 1 by 3. We're going to do element-wise multiplication of our vectors. So we'll take the first term multiplied by the first term, second term times the second term, third term times the third term, and we get that. And so if you look at this, if you look at just the nth row, okay, the result of this thing will be 2 by 3. And right now, as we have it, is we have a summation, and this will say, you do it for the first observation, you're going to get a 2 by 3. You do it for the second observation, you get a 2 by 3. You do it for the third observation, you get a 2 by 3. And then at the end, you take that 2 by 3 matrix, the first one, you add it to the second one, you add it to the third one, and you do it for all n of them. And the result is basically a stack of all of these 2 by 3 matrices that got added on top of each other. And the result is just a 2 by 3 matrix as well. And so that's what we have. We have a summation of all of these 2 by 3 matrices. Can we kind of make our life easier by getting rid of the summation? Because if we wanted to implement this in code as it's written, this would be like a for loop. For each observation in X, do this thing, get your 2 by 3 matrix, and then add it to kind of your running result. It would work, it would just be a little bit slow. And so we'll say, well, maybe we can take advantage of the fact that the computer likes working with matrices and vectors and can do element-wise multiplication. So instead of looking at just the nth row in X, I will take all of X. And so all of X transpose is 2 by n. Okay, instead of just looking at the nth observation in Y, which is just a 1 by 1 scalar, we will take all of Y, which is going to be this column of n values. Instead of just the nth observation in Z3, I'll take the entire column. And W, that remains. There's no, this doesn't change. There's not different observations of W2, so that's just going to remain 1 by 3. But here, instead of just the nth observation in Z2, we will take all of Z, which is going to be n rows times 3 columns. And so we can do this, changing the dimensions of this. I get this is 2 by n, this is n by 1 and n by 1, so we have to use element-wise multiplication for these to multiply. Here I have a 1 by 3, so that works out. This is n by 3. So this thing, n by 1 times the 1 by 3, this whole thing becomes n by 3. And then I can do element-wise multiplication with an n by 3. So I have this n by 3 matrix over here. I have an n by 3 matrix over here, and I'll kind of go element-wise across the first row, the first, second, third observation, next row, first, second, third observation, and I can do element-wise multiplication and do that. And then we can do matrix multiplication, a 2 by n times an n by 3, and that final result will be 2 by 3. Okay, so kind of just doing all of this. This is n by 3, element-wise multiplied. This whole thing is n by 3. 2 by n times n by 3 is going to be a 2 by 3, which is exactly what we want. We wanted a 2 by 3 matrix. We got a 2 by 3 matrix. Okay, and so that's what we have. We'll call this whole thing delta 2. And we are just about out of time. Okay, the next thing is, okay, we have all of this and we want to code it up. And surprisingly, or I don't know, maybe it's not surprising, but once you've done the math, coding it up is actually simple and straightforward. So, for example, the sigmoid function, you just have exactly that, 1 plus 1 over e to the negative z or t or whatever you want to use. Okay. A couple things here. Sorry, I'm just kind of skipping through this really fast. But this was our first kind of gradient that we calculated. We said A2 transpose minus y hat element y is f prime z3. We're going to call this part over here y minus y hat time element y is f prime z3 delta 3. And you can see when I code it up, I just write exactly what I have. Delta 3 is negative y minus y hat element-wise multiplication, which is just the star, times sigmoid prime of z3. Sigmoid prime is just the derivative function that we kind of wrote up it over here. Okay, and then dj dw2 is you take a2 and you transpose it, and now we're doing matrix multiplication times delta 3. Same thing with this thing. Here, this is delta 3 times w2 transpose element y sigmoid f prime z2, and then here I just do x transpose times delta 2. Okay, anyway, you can look over this code, and we'll go over it next week on Monday some more. And we'll go ahead and wrap it up here, and then I'll give you your final view quiz answer after I stop the